section 5.3, which is essentially what we did with Flip Math 5.9 yesterday. Same stuff, okay? But once again, this stuff is all over the AP test. There's going to be 5 multiple choice questions. 1 will be a calculator only one, so you'll have to be able to do things on the calculator to find those zeros where they, might have a relative max or min or a point of inflection. Like that's, I can guarantee it. There'll be 1 on a free response. They'll ask about this too. So, I'm willing to take plenty of time to get this all done. And this right here, this paragraph is a very good thing, particularly. It's extremely common. The free response question calculus test is one where a graph of a first derivative is given and students are asked to make conclusions about the original function. It's all over it. With justification, which is the important part, and it's a very specific way to justify things. It's very important that students reference the graph given by name in their justifications. Super important. If they call it G, you also call it, or they call it G prime because it'd be a derivative function, you also call it G prime, okay? Use the names that they've given it in your justifications. It's unnecessary and unwise to write more than a 1-sentence justification. It is. Yeah. Let's see the red box there. Oh, okay. Yeah. All right. But thank you. If a student justifies correctly but continues by writing a false statement afterward, then that justification point will be lost. So it's like, don't say too much, like if you keep talking, you're just risking a little false word, okay? So you want to say just the right thing, just a short sentence. And so that's what we're practicing today. So many students find it helpful to draw a first or second derivative number line, little sign charts. These number lines don't count as justification, but may help the student answer the question correctly, which is, of course, a priority. And not only that, but I do believe that the readers know what that means, and if it's labeled properly, they have a better idea of understanding what you're doing. Obviously, the more work that you show, the more they understand how you're thinking. But all right, so here we go. We have a lovely little graph. The graph below is a graph of a differentiable function. F prime is the derivative of the function y equals f of x. And we are looking at the graph of f prime. It has horizontal tangents, and this is an important part too. All the questions on the AP test always have a little paragraph to start, right? Take your time. Your test is digital, which is different than being on paper. On paper, I can go like, we've got horizontal tangents at plus or minus 2. I can underline, I can circle. You will have paper in front of you, so write them down. Make a sketch of the graph, okay? Take the time to look carefully and be like, okay, so at -2, I'm seeing that there's a horizontal tangent. Okay, that's good to know. And at +2, I'm seeing that there is a horizontal tangent there. So take the time to really understand. Maybe you can't write it down, but you can take the time to think it through. But as always, I definitely advise making a sketch. And its domain goes from negative to positive infinity. So it does continue on here forever. All right. On what open intervals is f increasing? What do you think? Okay, -4 to 0. Very good. And +4 to infinity. So what we want to talk about here is when we're looking at a derivative function, then the zeros of that function are very important to us. We see that we have zeros at -4, 0, and +4. So it might be worth it to make a little sign chart. To the left of -4, we are under the axis. We're in negative land. Between 4 and 0, we're in positive land. Between 0 and 4, we're back to negative land, and to the right of 4, we're in positive land. And when we're looking at the derivative, a negative tells us that f is decreasing, and a positive tells us that f is increasing. So it is, you can take the time to write these things down. And for now, first derivative, increasing, decreasing, max and min. Those are the things that we can find here. All right, so then we know he used the word open, which means we are going to just use parentheses here, not brackets. So increasing from negative 4 to 0 and 4 to infinity. Now, what's our justification? Very good. F prime of x is greater than 0. And what's really important here is that the graph that we're given is f prime. So every time we justify something, we have to reference f prime. I can't say because, I don't know, if this applied, f double prime is less than 0. I'm not looking at f double prime. I can only reference what is before my eyes, okay? You can't say because the y values of f are increasing. Well, there's no f function here to look at, so you can't use that. You have to justify with the graph they've given you. All right, that's perfect. On what intervals is f decreasing? Good. So the question here is, then we see f is decreasing negative infinity to negative 4 and also 0 to 4. We've already written that. Negative infinity always gets, or infinity always gets a parenthesis because we can never equal it. It is more correct to actually use brackets on increasing and decreasing because, if something is increasing, it's increasing because the y value is getting bigger all the way to that point where the slope is equal to 0. But still, that very last point is bigger than the point before, okay? And so it actually is most correct to use a bracket when talking about intervals that increase and decrease. Because, what's our justification? Okay. Now, here's what I am going to say about that, though. F prime of x, we're actually going to say is less than or equal to 0. The very most important thing is that we have agreement that if our bracket is allowed to be equal to, then shouldn't our also x value be allowed to be equal to 0? So we do include that. So we have agreement here that that bracket means equal to. We're going to use the less than or equal to as well. So it includes the whole interval. I would say this is what Gary Taylor uses for his reasoning. I think it will count, but I'm just going to add in here on those intervals. On those intervals. It's just a level of specificity that sort of increases it. Just that little statement on those intervals, all right? Just making it very specific that the derivative is below, less than or equal to 0 on these specific intervals, and that's what makes it decreasing, okay? I think both would earn credit on the AP test, but I know like one of the chief graders keeps harping on this. All right, it's just that little bit of being extra specific, but I think both would work. Okay, at what x values does f have a relative maximum? How do we know we have a maximum? Yeah, it goes from increasing to decreasing, and so we must have a maximum there. And is that the only place then? I think so. Okay, so at what x values? So we're going to say at x equals 0. Because, what do you think you should say? F prime of x changes from positive to negative. At that point. I don't know. Maybe you want to say at that point, but yes, f of x changes sign from positive to negative or changes from positive to negative, I think would work just fine. Okay. Maybe at x equals it. I don't know. You know, it's like how specific do we need to get? I don't know. Is it that little extra bit that, you know, you can't really sealing the deal there? All right. At what x values does f have a local minimum? Same thing. You'll notice Gary changed the word relative, local. They are the same. So where do we have a local minimum? Yeah, plus or minus 4. So once again, we're going from decreasing to increasing slopes. So that would give us a minimum. Decreasing to increasing, again, another minimum. All good things to keep in mind. So x equals plus or minus 4 because f prime of x changes from negative to positive. At those values. I don't know. Oh my gosh, values. Maybe you add that on, at those values. I don't know. They go through and they like pre-read all of the tests. So the chief readers get together and they go through and they read through like a whole bunch of the student responses and get a good sense of what kind of mistakes they're making. And then after they've read through like 1,000 papers, then they develop the scoring rubrics for these things. So I don't know, it's just good to try to get every single point we can. All right, on what intervals is f concave down? If we're talking about concave down, what derivative do we care about? The second derivative. But we don't have a second derivative, so we, again, have to reference the graph we're given. So in order to be concave down, that would be where the second derivative is negative, or where f prime is decreasing. Very good. So for the second derivative, we're talking about the slopes of this function. And you can reference it that way. You can say the slopes of f prime are negative. So you could say it that way, but I would, increasing and decreasing f prime is the best way. We can also make a little f double prime if we want to. Number chart here, sign chart. They told us that we had a slope of 0, horizontal tangent, at -2. So again, that's a critical value there. So I'm going to put that on my second derivative sign chart. And at +2 is another critical value. And we can see from our graph that we have positive slopes to the left of -2, and then negative, and then positive. So we have positive, negative, positive. And so again, this is just to help you. We know that for concave down, that's where our second derivative is negative. So concave down right there, concave up on either side. And then it just sort of helps to say, oh, well, I know it's concave down between -2 and 2. That's where my derivative function is decreasing, okay? So we're going to go with the interval. Now, I do use open intervals. They will never grade you. You will never lose a point because you used an open interval versus a closed interval, or vice versa. They never assign points to brackets or parentheses on an interval. And that's mostly, which is good news, so you don't really have to ask that question of yourself all the time. It's good news because really it comes down to, is that a bracket or a parenthesis? Yeah, right? Like, who's going to grade that? Okay, so, but we typically do use open intervals with concavity. So on the interval from -2 to 2, because f prime is decreasing, on that interval will probably be the best result. It would also, you could also say, because f prime has negative slopes on that interval. And that would be okay to say as well. It means the same thing. Decreasing talks about the slopes being negative. And so this is f prime has negative slopes on that interval. Same exact thing. All right. At what x values does f have a point of inflection? When do we get a point of inflection? When the, not specifically, not enough. That is part of a condition of being a point of inflection. So -2 and +2 are possible points of inflection. Yes, it does have to change sides. So it does have to change from increasing to decreasing. Oh, but you know what you could say? You could say x equals, here's one way you could say it, ±2, because f prime has a relative maximum or minimum at those values. So to have a relative max or relative min, we are changing from a positive slope to a negative slope. That would be where we would have a point of inflection, or negative to positive. So that's one way to say it. That's a great way to say it. So if the derivative has a relative max or min, that would be a point of inflection. Or we could also say because f prime has horizontal tangents and changes between increasing and decreasing. Increasing and decreasing at those points. That is obviously not as succinct. And changes between increasing and decreasing at those points. So relative maximum, definitely short and sweet, like it. All right. F prime has horizontal tangents and changes between increasing and decreasing at those points, which is important. Changes between, which goes either direction. All right, that's pretty tricky. All right, last one. On what intervals is F both decreasing and concave upward? 2 to 4 is one of them. All right, let's look. So to be decreasing, we know that f prime has to be less than 0. So looking at our picture, we would see where it's negative, below the axis. And to be concave up, well, concave up, we know from my sign chart before, I was concave up from negative infinity negative infinity all the way to 2. So I'm concave up, and this whole concave up, that whole region. So this whole region would also be concave up, where we're increasing. So let's see, to be concave up, f prime is increasing. So what we need is where is our graph negative and where is it increasing? So right here, f prime is negative, and also here f prime is negative. And so you can see sort of graphically looking at it, you can see where do they overlap? Where are we negative and our function is increasing? Negative infinity to -4 and 2 to 4. All right. We could combine a sign chart too. All right. So negative infinity to -4 and 2 to 4, because f prime is negative and increasing on those intervals. All right, because f prime is negative and increasing on those intervals. Negative gets the decreasing part, concave up is the increasing part. So, referencing the graph we've been given. All right, questions on those? Pretty good? Understand the justifying part? It's pretty simple, right? Like, that's what you'll see when I start handing out scoring guidelines. Everything is like super compact. It's like 12 characters, get every point you need. Like, so it's kind of neat. All right, so fantastic. You have some bookwork. Yeah, bookwork. I think, let me get it. Write it down for you. It is online, but. All right, we're going to do number 12, I think, together, but. So here we have assignment 5.3, 1, 2, 4 through 6, 8, 10, 12, and 17. Again, a lot of review in there. Check your answers in the back of the book for sure. And I want to show you number 12. So if you want to get out paper, we'll start with number 12 because it's just a really neat problem. And it ties into stuff that we're going to be doing later. Oh, Jesus Christ. Take care of my drinking problem. All right, so number 12. The function f of x equals 4,000 over 1 plus 100e to the negative 0.5x can be used to model how a disease spreads in an isolated population of 4,000 people. X represents the time in days. Always pay attention in word problems to what the variables represent, because it will always be used in your justification. Not only that, but just paying attention to, those units can answer a lot of questions or help you to figure out how to get to the answers. X represents the time in days since the sickness started, and f of x represents the number of people who have become sick, so the infected. Do you know what kind of curve this is? It has a very special name. It's called a logistics curve. So this is a calculator question. So we're going to go ahead and start by, graphing it. And a question like this, I want to do this because it comes to getting a proper window on in order to be able to see it. So first and foremost, what happens if you plug in 0 for x? This becomes e to the 0. What is e to the 0? 1. And so this becomes 100 times 1, which is 100. And so we get like 4,000 over 101. All right, so we get like 400. Okay. So when x is 0, our y value is like 400. Is a 10 by 10 window going to cut it? No. Okay. So I'm going to go ahead and type in. And again, this is a great question too, because it's really going to test whether or not you know how to plug it into your calculator. So I'm going to do it. Go ahead and plug it in how you think, and then we'll make sure you're right. All right. Did you put parentheses around the denominator? Because if you didn't put parentheses around the denominator, you just got it wrong. Super important. If you don't include the parentheses, then your graph is going to be 4,000 divided by 1, which is just 4,000, plus.
Just the fraction.
You can do that.
That's not,
yeah. But yeah, so yes, you can do that. All right. So we know that if I plug in a 0, I'm going to get about 400. So I want my window to go, for the y values, 400 is not enough. That's just the starting curve. And sickness is growing, right? So we would expect it to increase. But I'm going to go all the way up to 4,000. And then for my x max, this is that time axis. This is days from 0 onward. So I don't really care about the negatives. So I'm just going to go from like -2. And then, I don't know, I'm going to go to 20, let's say. And then graph. Do I need to go back to my window? Window settings. So on the window button, I'm going from -2 to 20 on the x-axis. And then up to 4,000 on the y. Okay, and so this is called a logistics curve. And a logistics curve it always looks similar to this. It's a very interesting curve, but we use it to represent all kinds of population growth. And it is quite a natural curve. We talk about it a lot when we talk about like ponds and fish. The population of fish in a pond starts out really low. And then the fish, have a population boom. And then what happens, they get to a certain point. And then the population of fish starts decreasing. Why would the population of fish not just continue to grow? They start eating each other. What about the resources within the lake? No, there's none left. They're eating it up, right? So they're running out of room. They're running out of resources to eat and start dying because there's not enough food for them to fill themselves up with, okay? Our logistics curve as humans will ultimately be this way too. Anyway, we get to see a lot of things here, namely that we start with pretty slow growth. And then that, tangents, don't go away. Okay. Imagine those tangent lines, those rates. We're talking about illness here, so same idea for the spread of illness here. The people infected per day is increasing, and it's increasing. And then right about here, we get what? Start slowing down. Yeah, we changed. You'll notice the graph is going from concave up, and it changes to concave down, all right? So we get this point of inflection here. This is the maximum rate of infection per day, all right? It's the steepest right at that point of inflection, and then it starts decreasing. Okay, that would be the rate of inflection per day is decreasing after that. All right, so that point of inflection in a logistics curve is very important. But you can see it caps out here about 4,000, steadies off, and that's that stable population sort of equilibrium. Okay, and you can see it in the curve. So just an idea, if you ever see something that looks like this, that 4,000 is a good number to use in your graph. All right. Okay, so part A, how many people have become sick by the 10th day? How are we going to answer that? What do we need to do? Plug in 10, yeah. So this is a time, so that's t equals 10, all right? And how many people have become sick? Well, that represents f of x. So this is really just f at 10. And this is the notation I would use if this was a free response question. I'm taking my function, I'm plugging in 10, and you guys can do that. Use your calculator. $23.89. Yeah, and change, right? So 2389.779. On the AP test, you always have to maintain at least 3 decimals. But of course, we're talking about people here, so what would be a logical answer? Yeah, 2390 people. Sick. So 2,390 people are sick on day 10. How fast was the disease spreading on the 10th day? What's that asking? How fast? That is the slope. Very good. How fast was the disease spreading? That is rate of change. All right? So that's asking a derivative question. That is, what is the derivative on the 10th day? And again, if we're thinking about our graph, if I make a little sketch here that we just had, it looks like this, right? And we've got infected, number infected, and days on your axes. And what we're doing is on the 10th day, we're finding that slope, the change in the number of people infected over days. That's infected people per day. All right, and so that's the question they're asking. And again, we can do this on our calculators. How do we figure this out on our calculators? Yeah, numeric derivative. So that'd be math 8. So we're going to do math option 8. So we want the derivative of y1 when x equals 10. And this is a required skill on the AP test. I guarantee you'll have to do it at least once, most likely twice. And we get 481.0089. And I would say infected per day. So 481 people are becoming infected every day. Seems like a lot, doesn't it? And a population 4,000 people. Yeah, it's crazy, right? Yeah. All right. Use the maximum function on your calculator to find the maximum point on f prime. All right, so the maximum point on f prime. We already have our function in here. We know that it's a logistics curve. And so what we want to actually do is we want to actually graph f prime. So I'm going to go ahead and do math 8 and graph the derivative. So we want the derivative with respect to x of y1. And we're going to do that for every single x value. This takes a while to graph, but we can go ahead and it'll show us that, and then we can use it to find the maximum. Let's see how it corresponds to our original curve then. Right? Because it's literally calculating slopes between a pair of points on their curve. All right, so let's look at how that corresponds. It looks like here's the max. Oh my God. Excuse me. So what does that maximum correspond to? The inflection point. Yeah, exactly. So that relative maximum on our derivative corresponds to that inflection point on our curve. Okay? So we can go ahead now and find that maximum. So we're going to do calculate. Calculate the maximum, number 4. Have you guys done that before? Okay, so right now Tinkerbell is on the blue curve, and I'm going to shift it using the down arrow to the red curve, so I'm on the right curve. And we got to go left a bit, hit enter, head right past it, hit enter, and then guess. Head to the maximum and hit enter. And so it tells us that the maximum is at day 9.2, 500 people have been infected. Let's see, x equals 9.210, y equals 500. You can round that up to 500, by the way. All right, so then it says, what does the y-coordinate represent? What does the x-coordinate represent? So the x-coordinate represents the days since the sickness started. So 9 days. I'm just going to put days on there. And then what's the 500 represent? So this is, again, yeah, we're looking at the derivative here of our curve. And so this is the maximum infected per day, right? Yeah. So the max infected per day. You are not technically allowed to do this on the AP test. Use that maximum, finding the maximum on the AP test. They will never ask it in a way for you to do it that way. So like we did the left and the right, and it's not, we'll never do it that way. You can't justify by saying I did it on my calculator, right? There's no calculus in that. All right, so that Y value represents that the disease is spreading the fastest at a rate of 500 people per day, people infected per day. So where it's spreading the fastest. How many people have caught the disease when the curve is steepest? Ooh, that's interesting. How do we figure that out? Original curve, very good. 9.21, we take that days and plug it into the F. So we really want F at 9.210. And so that'll give us the people on that, at that day. 9.21. Yeah. 1999.829. So about 2,000 people, I would say, about 2,000 people have been infected on the 9th day. Why would the slope of the curve decrease after a period of time? Because so many people have already caught the disease, it's finding it harder to find people who haven't yet, all right? They've got the antibodies already. They're reaching a concentration. All right. that's interesting. When was the rate? When was the rate of the spread of the disease increasing the fastest?
So wouldn't that be a double? Could it be double prime because it's infected per day.
When is the rate, so that definitely means another derivative, of the spread of the disease increasing the fastest? So that is another derivative to know when it's increasing the fastest. It's a rate of a rate of a rate. It is the triple derivative. That's kind of crazy. Graphically, all right, so the fastest increase of the rate of spread. So we are looking at the rate of spread, and then where is that increasing the fastest? That's a rate of a rate. So we're starting with the derivative, and then figuring out where that, so that's actually, which is crazy to think about, f triple prime of x, where it reaches 0, increasing the fastest. So that'd be where it's, peaking out somewhere relative max. It happens at x equals 6.576 days. I've never seen anything like that on the AP test, but this requires, doing another derivative and finding the max of that. So, all right, y'all, finish that up.